Assignment 10, question 1. Actually, you could do this question at the end. It's not that useful just to go through your resources and identify these equations. You really want to try and understand these equations, and then you should be able to identify them. So there are 8 equations. 3 of them are incorrect, and 1 is doubled up. And these are the 4. It's actually only 4 equations, and these are the 4 equations. Okay, I just added that text. So the only one of these 4 that you've seen before is Gauss's law for electric fields, and this Gauss's law for magnetic fields, and then the core subject of this week, Ampere's law and the Biot-Savart law. So look at your list of equations in front of you and see if you can identify any of them. This is Gauss's law for electric fields, and I added a little bit of symbolism compared to what's on your screen. This is a double integral because it's an area integral, and this is the definition of electric flux. Now, if we put this symbol in, it means the integral over a closed surface. So if we find the electric flux over a closed surface, it's that, and it will be equal to the charge inside over epsilon naught. So this is a relationship. Gauss's law for electric fields tells us something elemental about electric fields. It's a relationship between flux over a closed surface in an electric field and what's inside. So ask yourself, what is that fundamental quality of electric fields, that fundamental character of electric fields that this relationship captures? And you should explain that in words and with a diagram. And by the way, you can see question 1, I'm going to go through these 4 equations and spend a few minutes on each one. So if all you want is the answer to question 1 and to move on to another question, you can just scroll ahead. But I'm going to spend the next several minutes discussing each of these 4 equations. So here it is. Electric field lines begin on positive charges and end on negative charges. Notice, electric field lines begin on positive charges and end on negative charges. Very different from a magnetic field, right? As we'll see in Gauss's law for magnetic fields. Magnetic field lines have no beginning and no end. There are no monopoles. That's a really important distinction between the 2 kinds of fields, and it results in this relationship. And the best way to explain this is a final exam question maybe, explain Gauss's law for magnetic fields and electric fields, is a diagram of a dipole. So how would you do it? You have to draw closed surfaces. So draw several, 3 or more closed surfaces on this diagram that illustrates this point. Okay, at this point, let me remind you that flux is visualized through field lines, right? The word flux means flow. This field is static, but it looks like it's flowing, so we call it flux, even though it's static. And so the amount of flux, which is just the electric field times the area times the cosine of the angle, right, can be visualized in field lines. So if we take the red surface, it encloses a positive charge. 8 field lines leave, no field lines enter. That's a net large positive flux. Whereas the blue surface encloses half of the negative charge. 4 field lines go in, no field lines come out. So the amount of flux entering, it's negative charge, is half that for the red circle. So the amount of flux is proportional to the charge inside. And if we draw the green surface that doesn't enclose any charge, then you'll see 1, 2, 3, 4, 5 lines entering, 5 lines leaving. There's flux through the surface, but the net flux, the total flux through that closed surface, is 0 because there's no charge inside. So the fundamental relationship is, expressed in Gauss's law, is that field lines originate on a negative charge and originate on a positive charge and end on a negative charge. Now let's go to the magnetic field. Here it is. I changed it a little from what's on your screen, but I wrote down that the magnetic flux through a closed surface, that would be this, and I wrote it as a double integral. It's okay, you can write it as a single integral, but you do want this circle indicating it's an integral over a closed surface of the same dot product, B dot dA. And let me remind you that that product is, it's a vector. I should have vector symbols in there. It's the magnitude of B times, that's what the dot product is, times the magnitude of dA times the cosine of the angle between them. And I'm not going to review that now, but you should understand that relationship and how that leads to the amount of flux passing through a surface. Anyway, the essential thing about this is that that is always zero, and that's simply an expression of the fact that magnetic field lines have no beginning and no end. Let's draw a diagram to illustrate that. Try drawing one. Draw the field due to a current carrying wire, and then draw some closed surfaces. Actually, I changed my mind. Since we just did a dipole, here's a magnetic dipole. Now draw your closed surfaces. So notice the difference between this and the electric field. Clearly the green one, drawn in the middle, if we took the time to count, every field line that enters leaves, and it's easy to see. But even in the case of the red one, notice this field line enters and leaves. This field line enters and leaves. They have to, right? They don't terminate anywhere. And the north pole of a magnet is simply the end of the magnet where the field lines leave, and the south pole is the end of the magnet where the field lines enter, but they don't terminate there. They go right through in continuous closed loops. And so this picture could be a dipole magnet, a bar magnet, or it could be an electric coil carrying current, right? It would have the same kind of field. So that's the essential feature of Gauss's law for magnetic fields. Okay, let's look at the wire. So here's a wire and a magnetic field. Can you tell? So I drew a big wire. I'll explain, you'll understand that later. And the dots, right, are vectors coming towards us. So the current's coming out of the page, all through the wire, and this is the magnetic field around the wire. By right-hand rule number 2, it's counterclockwise. The blue lines are field lines, and they should be perfect circles. They're not, but they should be. That's the magnetic field. They're closed loops. And let me just say something. I think diagrams are essential to our understanding, and you should draw them. So don't get in the habit of just doing assignments and not actually writing out equations. You should keep a notebook, a piece of paper or something with you, and you should be drawing diagrams and writing equations. So anyway, here's our diagram. And if we apply Gauss's law to this, Gauss's law for magnetic fields to this, you'll see no matter what closed surface you draw, the number of field lines entering and leaving will be the same. In other words, there's no way of drawing a closed surface that will have a net flux through it. Notice, in fact, if I draw a closed surface here, remember, we can choose any surface we want. And remember, this is three-dimensional. So the surface has to be closed. It's actually the wire is going to go in and come out. But you can see that no field lines enter or leave. So that's clearly zero. But if I draw a closed surface over here, 3 field lines enter and 3 leave. So notice if I draw the surface that encloses the wire, and draw it as a sphere, there's no flux. But anyway, in either case, the flux, as Gauss's law says, is going to be zero. But because a magnetic field has this closed loop, curled quality to it, there is something we can do. And remember, once again, these surfaces that we're drawing for Gauss's law are closed surfaces. Now we're going to switch to Ampere's law and watch this. So Ampere's law, different from a surface integral, right, where you're integrating some quantity like the electric or magnetic field over area elements over a closed surface. Here we're doing a line integral. So we're going to draw a closed loop, and this is really like a one-dimensional line, closed loop, and we're going to do this integral. And if this integral encloses current, then it will have this value. Very similar to Gauss's law for electric fields. But if it doesn't enclose any current, it's going to be zero. So let's put some loops in our diagram and see what happens. So I've constructed two random loops, and remember, this holds true for any closed loop. You can choose any you want, and what you're going to see is there are certain ones that make this integral easier to do. So anyway, here's random loop number 1. And remember what the line integral is. It means that we're going to go around the loop, and at every point on the loop we're going to take a small displacement vector, or ds, and we're going to evaluate this dot product. Now remember what that is. That's the magnitude of b times the magnitude of ds times the cosine, that's the dot product, cosine of the angle. So notice if I take a ds here, in this part of the loop it's going up, I'm integrating counterclockwise, and the field, if you look at the direction of the field is also up. So those two vectors are in the same direction, and the cosine is 0, and we'll get a positive value. However, when you go over here, going around the loop, the ds is down, the b vector is still up, and it's the cosine of 180, and this will give us a negative value. If we take a ds vector here, the field is up, they're perpendicular, the cosine of 90 is 0. So I don't know if you can see, but as you integrate around this loop, you're going to get positive 0 values and negative values, and they're going to cancel out. It's going to be 0. That may not be easy to see, but the whole concept of the line integral is important that you understand. Now if we take this loop, the one that this surrounds no current, so by Gauss's law we expect it to be 0. This surrounds current. So this should have a value which is equal to mu naught times the current enclosed, only the loop I've chosen is going to be difficult to integrate because at this point here, if I choose a ds, it's up, and the b is up, and so that's the cosine of 0. But when I get over here to a ds, the ds is always along the loop, right, tangent to the loop at a point. The b is this way. Now we have to know this angle, and so on. Here's a ds, here's a b. So there's all these different angles. This line integral would be very challenging to calculate. So what we do is we choose a loop that's going to be easy to do the integral. And what would that be? That would be a loop that follows the symmetry of the magnetic field. So logically it makes sense to choose a loop which is a circle, which follows the field around. And now if I want to do this integral, right, everywhere, because it's a circle, the value of the field everywhere on this circle is going to be the same value because I'm the same distance from the center of the loop. So by symmetry, whatever the value is, and we're pretending we don't know it, it's going to be a constant value. So that can come out of the integral because it's constant. And the angle between any ds that I might draw, if I draw a ds here, the field is parallel to it. If I draw a ds here, the field is parallel to it. And remember, what we're doing with the integral is we're doing an infinite number of ds's all around the loop and adding them up. That's what the line integral is. And so this equation simplifies. B is going to be a constant. All we have to do is integrate all the ds's around the loop, and they will be equal to mu naught I, the current enclosed according to Ampere's law. And so if we add up every ds around this circle, what are we getting? We're getting the circumference of the circle. So this equation becomes B times 2 pi r, the radius of the loop that we're integrating, equals mu naught I. And so this gives us, we just derived the equation for B due to a current carrying wire. It's going to be mu naught I over 2 pi r. See how easily that comes out of Ampere's law. Well, easy. If you understand the line integral and you understand Ampere's law and you know enough to draw a circular loop around the wire. Now there is another application. Supposing we wanted to know the field inside the wire, we would do the same thing. We would draw an Amperian loop or a circle inside the wire. And in that case, as we integrate it around the loop, only the current inside the loop would be included in the I. And I'm not going to work that through, but that leads to a result, a very simple result, that gives us the magnetic field inside a current carrying wire. So there's two applications of Ampere's law, and notice how the law works, and you should be able to answer question 2. Notice the ds vector is on the loop, it's not in the wire, and this is in contrast to Biot-Savart law, which we're going to do next. Before we go there, we can eliminate 2 incorrect equations. Notice on the top we have Gauss's law for electric fields, and that is Q inside over epsilon naught. We know that. So there's one equation that has E dot dA equals mu naught I. No, that goes with Ampere's law. So if we put these two together, it's wrong. And the Gauss's law for magnetic fields is 0. But if you look, you'll see one equation with B dot dA equals to mu naught I. No, that's Ampere's law. It's very similar, right? If I change this to an S, it's correct, but if it's an A, it's a surface integral, and it's incorrect. So those are 2 of the 3 incorrect equations. Now we can go to the Biot-Savart law. So Ampere's law is fundamental to our understanding of magnetic fields, but for calculating magnetic fields, it's only useful in a few high symmetry cases. The Biot-Savart law, on the other hand, can be used on a very, very wide variety of cases, and so we can do the straight wire. We do a current loop. We can do a current loop at the center. We'll solve the problem like in the lab for the Helmholtz coils. What's the magnetic field of a current loop if you're on the axis of it? And many other situations. Let's look at the segment of wire I just drew and find the field due to a segment of current carrying wire. So the magnetic field due to this segment of current carrying wire is, as you might imagine, it's going to be different at different points in space. So if we pick a point close to the wire, it's going to look pretty much like a long straight wire. B equals mu naught I over 2 pi a, because from that point it looks like a wire. If I pick a point further away, then the wire is not really very long. But let's pick something that's even more challenging. Let's find what is the magnetic field at this point. What's B here? So the Biot-Savart law tells us how to do this. We take any place on this wire, we take a small segment of wire. Let's say right here. And this little segment we call ds. And it contains a current I. And for this little piece, we can get the field at that point by using the differential form of the Biot-Savart law. And I'll write that down. And here we have it, the differential form of the Biot-Savart law. And what it says is that if you take a little piece of a wire segment, a ds, with a current I, you can find the field at some point. It will be equal to the I times the ds times a position vector that tells you where the point is located. So there's an r hat here that gives us the direction from the ds toward the point we're evaluating. And it's going to depend on the distance, this distance r, the distance away it is squared. So it kind of makes sense, right? We know a point charge has a field and a force which depends on 1 over r squared. So the field is going to get weaker as 1 over r squared. But notice the ds is crossed into the r hat. And what that means is that if the point were over here, the field would be 0. You know, if we took a circle with this distance, the point would have its maximum value up here if it were straight along perpendicular to the wire. And even though we don't change the distance, that field gets less and less because of this cross product. Because remember, well, let me draw in that r hat vector. So r hat is a unit vector from ds toward the point that we're evaluating the field at. So that's r hat. And the angle between the ds and the r hat is our theta. And so remember, ds cross r hat, unit vector r, is the magnitude of ds times the magnitude of r hat. Well, it's a unit vector, so it has a magnitude of 1, times the sine of the angle. So there's where you can see if we put a point over here, the r hat vector would be in the direction of this, and the sine, the angle would be 0, and so there's no field here. But if the r hat were pointing to a point up here, then the angle would be 90 degrees, and we would get a maximum field value. And yes, one more item. How about the direction of the magnetic field? So remember, the ds, the cross product, is right-hand rule number 1. So if you point your index finger in this direction, and you point your other fingers in this direction, then your thumb points up. So that tells us that the field at this point is coming out of the screen. So what we found is at this location we're finding a dB. That means a little tiny magnetic field contribution due to this little ds. But to get the field due to this entire wire segment at this point, we have to integrate both sides of that equation, and that gives us the integral form of the Biot-Savart law. So see if you can follow this. In other words, we take all possible dBs, we divide this wire into an infinite number of infinitesimal ds's, and we add them all together. So B, for this entire length of wire, at this point, will be the sum or the integral of all the dBs. And that's a calculus problem evaluated from whatever the limits are to one end of the wire to the other. That would be the limits of integration. And we evaluate this integral where ds is ds times 1 times the sine of the angle between those two vectors. And so you should notice that we would start with the ds at this end and then do all the ds's all the way from there all the way to the other end. And so notice that the unit vector r hat is going to be, it points toward the point, right? The r hat is the unit vector that goes from ds toward the point. That's going to form a different angle. And also, the distance from this ds to the point, the distance from this ds to the point, and the distance from this ds to the point is a different r. So the angle is going to be changing and the r is going to be changing. It turns out this integral is quite doable, even with your skills from Calc 2, but not that easy that I'm going to do it here. So anyway, there's the second form of the Biot-Savart law. And what you'll see is since S cross R hat is S times 1, the magnitude of R hat times the sine of the angle, you'll see one equation in that list of equations in the first question that has the cosine of the angle. And so if you have the cosine there, that means this is an incorrect equation. So the Biot-Savart law shows up twice. This shows up once. This shows up once. That once. That's the 5 correct equations and 3 incorrect equations. Also, everything I've said about Ampere's law and Biot-Savart law should enable you to answer questions 2 about Ampere's law and 3 through 5, I think, regarding the Biot-Savart law.